In 1977, NASA launched the twin Voyager probes, Voyager 1 and Voyager 2, on a mission that began with a grand tour of the outer planets. Nearly 50 years later, these spacecraft have revealed a startling discovery at the very edge of the Sun's influence. A blazing wall of fire. This isn't fire in the traditional sense, but a zone of superheated plasma measuring between 54,000 and 90,000 degrees Fahrenheit, detected right at the heliopause, the boundary where our solar system ends and interstellar space begins.
The heliopause is an invisible frontier. Inside it, the sun's solar wind, a constant stream of charged particles, dominates. Beyond it lies the interstellar medium, the thin mix of particles and magnetic fields that fills the galaxy. For decades, scientists assumed this transition was clean and predictable, almost like crossing an invisible border. But when Voyager 1 crossed the heliopause in 2012 and Voyager 2 followed in 2018, the data told a far stranger story. Instead of a neat handoff between solar and interstellar space, both spacecraft found themselves in a turbulent plasma zone with extreme temperatures, reaching 30,000 to 50,000 Kelvin. This wall of fire isn't a wall in any physical sense, nor is it burning in the way flames consume matter on Earth. The particle density in this region is astonishingly low, far emptier than the most advanced vacuums we can produce in laboratories. Heat doesn't spread the way it does in our environment. Instead, the few particles present are moving with tremendous velocity, and their energy is what registers as these extreme temperatures. So, what drives this phenomenon? Scientists believe it stems from two key processes. First, plasma compression. As the solar wind crashes into the interstellar medium, it slows and piles up, forcing the plasma into a narrower, more energized state. Second, magnetic reconnection. When magnetic field lines from the sun and from the galaxy twist together and snap apart, they release bursts of energy that heat the surrounding plasma. Together, these forces create the persistent high-temperature zone that the Voyagers detected years apart. What makes this discovery so important is its confirmation. Voyager 1's observations could have been dismissed as an isolated anomaly, but when Voyager 2 entered the heliopause 6 years later and recorded nearly identical conditions, it proved this wall of fire is not a fluke, but a stable, enduring feature of our solar system's boundary. Even more surprising, both probes found that the interstellar magnetic field outside the heliopause appears aligned with the sun's magnetic field inside it. While these revelations already challenge decades of heliophysics, they also raise profound questions about the very nature of cosmic boundaries. For much of modern astronomy, borders in space were imagined as clean divisions. Solar wind here, galactic medium there. But what the Voyagers uncovered suggests something far stranger. The cosmos does not respect neat categories. Instead, the boundary is alive, bending and flexing under competing forces, almost like a cosmic weather front. Imagine the edge of the solar system not as a wall, but as a stormy coastline, where waves from the galactic ocean crash endlessly against the outward tide of the sun. At times, the sun pushes hard, inflating the heliosphere outward. At others, the galactic forces bite back, pressing inward. This constant tug-of-war means the heliopause is not a fixed distance but a living frontier that shifts with solar cycles and galactic conditions. If our solar system's edge is this dynamic, then the protective bubbles around other stars must be just as complex. That realization forces astronomers to rethink what it means for planets to be shielded from cosmic rays, and whether the safe zones for life are more fragile and variable than anyone once believed. This alignment was not expected. For decades, researchers assumed that the galactic magnetic field and the sun's field would be oriented differently, reflecting separate domains. Instead, the data suggest a kind of magnetic continuity, a handshake between our solar system and the wider galaxy. This raises new questions about how far the sun's influence might really extend, and how the galaxy itself shapes conditions at the solar system's edge. Until now, the heliopause was thought of as a relatively calm shield, a static barrier protecting the solar system from the harshness of interstellar space. Voyager's discoveries reveal something far more dynamic. The heliopause is not a quiet wall, but a restless, turbulent interface where galactic and solar forces collide. The heating observed there challenges long-standing models of heliophysics and suggests that massive magnetic reconnection events may be taking place regularly. These events could help explain why both probes detected bursts of energetic particles in the region, particles powerful enough to cross boundaries thought impenetrable. The magnetic field alignment adds another layer of mystery. Why are these two seemingly separate environments so closely linked? One possibility is that the Sun's magnetic influence extends farther than models predicted, subtly shaping the interstellar field nearby. Another is that the local interstellar magnetic field is more organized than previously believed, adapting to align with the Sun's field. These details matter because they affect how cosmic rays, high-energy particles from distant astrophysical events like supernovae, enter our solar system. The heliosphere, inflated by the solar wind, acts as a shield against many of these dangerous particles. If the heliopause is more porous or dynamic than once thought, it could alter how much cosmic radiation reaches Earth and the planets. This has implications for astronaut safety, satellite operations, and even long-term climate models influenced by cosmic radiation. Beyond theory, these findings are vital for the future of exploration. Any crewed missions that one day venture beyond the heliosphere will need accurate predictions of radiation levels and plasma conditions. NASA's upcoming Interstellar Mapping and Acceleration Probe, or IMAP, scheduled for launch soon, is designed to follow up on Voyager's discoveries. Equipped with advanced instruments, IMAP will study how the solar wind interacts with interstellar space, mapping the boundary region in unprecedented detail. Its results will not only refine our understanding of the heliopause, but also guide the design of future interstellar probes. The broader implications stretch far beyond our Sun. If the heliosphere interacts with the galaxy in such a complex and energetic way, then other stars' protective bubbles may behave similarly. By studying these processes, scientists can learn how stellar systems shield their planets from radiation, knowledge that plays a role in understanding habitability and the potential for life throughout the galaxy. And through it all, the Voyagers continue to astonish. Built in the 1970s, long before personal computers and the internet transformed daily life, these spacecraft remain humanity's furthest-reaching emissaries. Even now, billions of miles from Earth, they continue to send back data that reshape our cosmic perspective. NASA has already begun conserving their limited power by shutting down non-essential instruments, but both probes are expected to keep collecting critical measurements at least through 2026. Nearly 5 decades after launch, the Voyagers are still expanding the boundaries of human knowledge. They have revealed a fiery plasma barrier at the solar system's edge, uncovered unexpected magnetic connections with the galaxy, and raised new questions about how our Sun interacts with the universe beyond. And yet, these discoveries may be only the beginning. What other secrets lie hidden past the heliopause? What surprises await in the true interstellar medium? Thanks to 2 spacecraft launched in the age of typewriters and vinyl records, humanity is closer than ever to finding out. The frontier is still ahead, and the Voyagers are leading the way.